Okay, so for lesson 2.2, we're going to continue talking about functions and properties of functions, particularly with regards to looking at the graph of a function. So the first concept I want you to be aware of is how to describe when a function is either increasing, decreasing, or constant over its domain. So first of all, what do we mean by these three terms? If you look at the first picture, this is an example of a function that's increasing because as you read the graph from left to right, what is the graph doing? It's rising or going up. So we would say this graph is increasing over that interval. The second graph is decreasing because as you read from left to right, it's falling. And then the last graph is constant because as you go from left to right, it remains at a fixed value, a horizontal line. When you talk about these and you describe them over different intervals, you want to be sure you're describing them over intervals of their domain. So specifically, you're only going to refer to x values. Don't forget this point because that's what a lot of students miss. Let me give you an example. So take a look at picture A. It says describe where the function is increasing, decreasing, or constant. And so start by reading the graph from left to right. In picture A, think about what is the behavior of the graph doing to start off. Hopefully you see that it's decreasing. So what interval is it decreasing over? Well, remember, we're only looking at x values. So this graph, the arrows of course mean it keeps going. It's going to keep going up, but it also is going to keep going out in the x direction towards negative infinity. So we would say from negative infinity up to, where does that behavior change? Where x is 0, the graph is decreasing. And then what kind of behavior does the graph switch to? Switches to increasing from 0 up until about this point right here. Now remember, you're only talking about x values, so you're going to say from 0 to 2 because that's where the behavior changes again. And then from 2 to positive infinity, because now the x's over here are positive, so 2 to positive infinity, it switches back to decreasing. Here that all is written out so you can see it. So we're going to use interval notation to describe these. So like we said in the beginning, it's decreasing from negative infinity to 0, then it switches to increasing from 0 to 2, and then back to decreasing from 2 to infinity. How about for picture B? So it starts off constant, so the interval we'd say for constant is from negative infinity up to, where does the behavior change? Where x is 0. And then it switches to increasing from 0 to positive infinity. So here that is an interval notation. So constant from negative infinity to 0, and then pick up where the last interval left off and say it's increasing from 0 to infinity. Now one thing you may notice or be asking about is how do you know whether to use brackets or parentheses on these? I see that there's a hole here and then a filled in circle here, for example, in this graph. It does not matter. When you're talking about increasing, decreasing, or constant, we always use parentheses just as a matter of convention. On a test or something, if you slipped up and put a bracket in one of those spots, that would be okay as long as it's not one of the infinities. But I think my math lab probably will care. So make sure you use open interval parentheses for all of these when you do increasing, decreasing, and constant. Okay, the next term I want you to be familiar with is a relative maximum or a relative minimum. You've seen these before, you just may not have heard this term. A relative maximum you can think of as a peak in the graph, so a high point in the graph, and then a relative minimum you can think of as a dip or a valley or a low point in the graph. Let me give you a picture of this. So take a look at this graph. We've got a relative maximum and a relative minimum. So over here on this side we have a relative maximum because there's a peak in the graph. Really what's happening is the graph changes from increasing to decreasing. So when a graph goes from increasing to decreasing at that point, we consider that a relative maximum. And then over here it switches, you notice there's a dip in the graph because the graph goes from decreasing back to increasing. So we would consider that to be a relative minimum. Now these are ordered pairs. A lot of times though they'll say what is the maximum or what is the minimum, and they're referring to the y value. If they say where does that occur, they're asking for the x value. So let's look at this first point over here. We have a relative maximum. It's hard to see in the homework, it shouldn't be so ambiguous, but it looks to me that this occurs maybe at -1,8, somewhere around there. So we could say that the relative maximum of 8, the value, occurs at x equals -1. And then over here we have a relative minimum. It looks to me like it's at 2, maybe 2, -4. So we would say the minimum is at -4. I'm sorry, the minimum of -4 occurs at x equals 2. And that's all we're going to do with those. So you could write them as an ordered pair, but if they ask for what is the maximum or the minimum, remember they're asking for the y value. If they say where does it occur, they're asking for the x value. The next important concept in this chapter is piecewise functions. So a piecewise function is exactly what it sounds. It's a function that's broken up into different definitions or different pieces depending on which part of the domain we're talking about. So make sure you take good notes on this. This example, they're giving us a function, they're calling it c of t, and they're saying if the t value, the independent variable, is between 0 and 60, then we're just going to default to the constant function 20. If the t value working with is greater than 60, then we're going to use this function, this 20 plus 0.40 times t minus 60. We're not going to do any graphing with this, but we will be asked to evaluate some of these. So if I were to ask you what is c of 30, the first thing you want to do is look at the x value. The x value is 30, or the t value, I guess, is 30, and ask yourself which part of the domain does that fall into. So hopefully you see 30 falls into this first part, this top piece of the domain, because it's between 0 and 60. So the y value that goes with the t value of 30 is just going to be 20, because that was the constant function 20. Now what about if they ask us for c of 100? So this time 100 is greater than 60, so we're going to be working with the bottom piece, so the second piece of this function. So I'm going to take the 100 and I'm going to substitute it in for t. And you notice I got a value of 36 because I plugged it into the second piece. The one thing I want to be really clear about piecewise functions is that you're only working with one piece of the function at a time. These are two separate questions. They asked us for c of 30, we use the top piece. They asked us for c of 100, we use the bottom piece. You don't plug in the number into both functions. That's what or both pieces of the functions. That's a lot of students make a mistake with. You plug it into one piece or the other depending on which part of the domain the t value or the x value would fall into. Let's do another example. So this time we have the function f of x equals x squared minus 25 divided by x minus 5 if x is not equal to 5. If x happens to be 5, use the bottom piece, which is just the constant function 10. So they ask us for f of 0. So think about 0. Which piece of the domain would that fall into? Well, 0 is not the same as 5, so we're going to use this top piece. So we're going to substitute in 0 into that top piece, and we get a value of 5. If they happen to ask us for f of 5, where x equals 5 here, we would use the bottom piece and just get a value of 10. The next major topic is looking at symmetry of a function and how that relates to something called even and odd functions. So the first definition here I want you to be familiar with is even function. So a function is even. One way to tell it's even is if it's got y-axis symmetry. And vice versa, if a function has y-axis symmetry, you know it's even. So what do we mean by y-axis symmetry? We'll look at this graph here. If we take the function on the left side in the second quadrant and we reflect it over the y-axis, we get what's in the first quadrant. So that means it's got y-axis symmetry. A function that is odd would have origin symmetry, and I remember this because the O's go together, odd and origin. A function that has origin symmetry would, whatever's in the first quadrant should be reflective in the third quadrant. So it literally reflects over the origin. Or if you had something in the second quadrant, it would be reflective into the fourth quadrant. How can we tell what kind of symmetry a graph will have without actually looking at the graph? So if we're just given the function in equation format, how could we tell what kind of symmetry? That goes back to determining whether the function is even or odd. And so this is an important definition. We're going to use a three-step process to evaluate these, so take good notes on this. So a function is even, so I'm calling it f. The function is even if f of negative x equals f of x. In other words, if I were to substitute negative x into the x values and I simplify it, do I get the same thing as the original function f of x? And if I do, then it's an even function. function is odd if when I substitute negative x in and I simplify it and clean it up, I get the same as negative f of x. I know it's a little confusing. We'll do some examples. All right, so the question would say identify the function as even, odd, or neither. A function can be neither because it may not have symmetry. It may not be y-axis or origin symmetry, and if that's the case, it's neither. But let's try one here. So say the function is f of x equals 3x squared minus 2. So I always check these in a three-step process. The first thing I do is write down the function. So I put a little 1 next to the original equation. So f of x equals 3x minus 2 with a 1 next to it. That's step 1. Step 2, I check to see if it's even. So the way I do that is I substitute negative x in for the x. So then I write number 2, f of negative x equals, and then wherever there's an x, replace it with a negative x. Be sure you use parentheses. Now simplify this, and remember when you square a negative number, it becomes a positive number. So what I want you to notice is that f of negative x, after I made some simplification to it, is the same as the original f of x function. Take a minute and make sure you see that these two things are the same. Well, remember, that was the definition of an even function. The definition said that f of negative x had to be equal to f of x. So since those two things are the same, that means we're dealing with an even function. If you were asked what kind of symmetry it has, you would say it has y-axis symmetry, because even functions always have y-axis symmetry. Here's a picture of it. You don't have to know how to graph it right now, but there's a picture of it so you can see that it's got the y-axis symmetry we were talking about. Let's try this one. Identify this as even, odd, or neither. So step 1, of course, is to write the problem down in its entirety. So f of x equals x cubed minus 6x. All right, step 2, same as before, we're going to replace all the x's with negative x's. So I have f of negative x is equal to negative x in parentheses cubed minus 6 times negative x. Now, what happens when you cube a negative number? It stays negative. Negative 6 times negative x gives me positive. So when I simplify this, I get this. Now pause for a minute and ask yourself, does this match step 1? So in other words, does f of negative x match f of x? If it did, we'd stop here and say it's even, but hopefully you see that this does not match this. So then we go with step 3. We want to check to see if it's odd. So the way we're going to do this is we're going to see what negative f of x is. Now be sure you're clear on the difference here. In step 2, I was replacing x with a negative. In step 3, I've got the negative in front of the original f of x function, not the one from step 2. So what this means is I'm going to negate f of x. I'm going to negate the whole function. So I put negative in front, put parentheses around the entire function because that negative has to be distributed. Then go ahead and simplify that, and we get this. Now take a minute. What do you observe? Step 3 is the same as step 2. So remember, step 2 was f of negative x. So what are we saying? We're saying that negative f of x is the same as f of negative x. Go back and look at the definitions you just read down for odd functions. That was the definition. So if step 3 matches step 2, it's an odd function. What kind of symmetry would this graph have? Well, remember, odd functions always have origin symmetry. And here's a picture of it. So hopefully you can see it's got origin symmetry. The first and the third quadrants are reflected, and the second and the fourth quadrants are reflected. Let's do one more. Identify the function as even, odd, or neither. So step 1, of course, is to write down the original function. Step 2, remember, was to replace all the x's with negative x. So make sure you write this exactly how I've written it. F of negative x equals 3 times negative x squared minus negative x to the third plus 1. Simplify that. So when we square the negative x, it'll become positive. When we cube the negative x, it stays negative, but there was a negative in front of it. So make sure you see where we're at. 3x squared from the first term negative x to the third became negative x to the third, but then there was a negative in front of that, so that second term became positive. Does this match step 1? No, it does not, so it's not even. So we're going to go on to step 3 and check to see if it's odd. So step 3, remember, is to negate the original f of x function. So I'm going to put a negative in front of the original f of x, put parentheses around it because that negative has to be distributed, and simplify that. Does that match step 2? No, it does not, so this would be neither. So if step 3 does not match step 2, then it's neither. Has no symmetry, it's not even nor odd. Here's a picture of it. You can see it doesn't have any y-axis or origin symmetry.